Our next math topic is one that is actually a combination of a few different topics, and I hope you'll see why we put all of these together. We are going to talk about prime numbers. We're going to talk about modular arithmetic. We're going to talk about the GCD operations, including the extended Euclidean algorithm. And as a result of that, we will talk about Diophantine equations. And then finally, we will briefly talk at the very end about the Chinese remainder theorem. So it might not be obvious how all of these things are related to each other, but I'm going to go through each of them so that you can see them. Now, probably the least related of all of these is the first topic, and that has to do with prime numbers. And finding primes has been it's a long-standing problem in math and computer science. There's nothing new about this. The way that is commonly used to compute prime numbers is what is known as the sieve of, and then I always mispronounce this name, but Aristophanes. I think I have that spelled correctly. And basically, this is a process for generating primes up to a particular value. I intend to actually show an example of this being coded up separately, so you can look at that example to see how this works. But the basic idea of the sieve of Aristophanes is that we just start out with all of our numbers that we have. So I'll start with 2 because that's the first prime number, but I actually have a list of all numbers, period, up to some value that I want, and that value might be, I don't know, 1,000,000 or something. Okay, and you go through and you identify each one as either prime or not. So you keep a Boolean value for each value in an array. And if you come across a prime number like 2, one that is prime, well, then you mark every other number that is that is a multiple of that value as not prime. So since 2 is prime, we mark 4, 6, 8, 10. Basically, we're going to mark all of the even numbers as not prime. We come to the next thing. It has not been marked not prime, therefore it's prime. And so now we're going to take every multiple of 3 and mark it not prime. So there were 6 and 9 and 12 and 15 and 18. Okay, we come to the next number that is 4. However, that one is not prime. The one after that is 5. So we mark multiples of 5 as not prime. So there goes 10 and 15 and 20, which were already marked that way. We come to 7. 7 will allow us to mark number 14 as not prime. We come to 11, 13, 17, 19. All of those are going to be prime for this very small set that we have, but we'd have to mark more later on. And as we discover prime numbers, we can keep them in a list if we want to. We can just store this data as, which things are or not prime so that we can look it up later. And probably the use of primes, I think, are pretty obvious to most people. You all learned prime factorization back in elementary school, and prime factorization is often a part of a lot of programming problems where you have some very large number and you need to break it down into prime factors and do something with the primes. And you can use that to find things like a greatest common divisor, potentially, if you identify overlapping primes, although that's not the method we're about to talk about. You could use this in some of the methods that I'm about to show you toward the end, like the Chinese remainder theorem. There is a way of actually basically using primes as a modular base, and that will tell you whether numbers are the same or not. So process of generating and using primes, it's common. It's something that you should get used to being able to do. So we'll see one quick example here in just a minute, but first of all, I need to go through a little bit about modular arithmetic. Okay, so we're modular operations. So the idea of modular arithmetic is that you can perform operations modulo something and everything is closed. And there's a whole bunch of sort of mathematical algebra related to this. You can get a lot deeper into this if you want to. We're going to see several examples of this and how it's used here. But the basic idea to think about is if I have numbers A plus B, and I'm going to take them mod some value, and let's just call that C. That's equal to A mod C plus B mod C, and the whole thing mod C. Okay, and the reason why we want to do modular arithmetic is that every number is guaranteed to fall in the range of 0 to C minus 1. So when we have a modular base C, every number that we get modulo that is between 0 and C minus 1 by definition. And so this means that we have a cap on how much memory we need to store something. So we don't have to worry about if a number is too large or if the number is going to overflow, because in the end, everything is no bigger than C. And in particular, if we want to be able to perform operations, well, if we're doing something like addition here, where we add two numbers together, all we need to do is be able to temporarily hold the sum of two numbers, each one of which is no bigger than C minus 1. And then we take the modulus and we get the result. There have even been computers developed in the past that incorporate modular arithmetic into the hardware itself. And I don't think any of the current systems do, at least that I'm aware of, although they might. But modular arithmetic, other than, I should say, there are some where like the base 2, just the way it handles overflows and things effectively does that. But as far as a general operation, I'm not aware of current hardware supporting that. However, it wouldn't surprise me if maybe it's there. And there's definitely older hardware that supported that. So the idea, though, is that this helps give you a cap. Now, if you can do the same thing if you're wanting to multiply two numbers, A and B mod C. Again, it's the same as A mod C times B mod C. And then the whole thing, again, mod C. And the point here is each of these numbers is going to be no bigger than 0 to C minus 1. And so if you multiply these two things together, the product of them is going to have no more than twice as many bits there. Okay, so if C requires n bits, then the product requires no more than 2 n bits. Okay, so if C is of n bit size, then this is no more than 2 n bits. And so if you imagine that like C is an integer, well, all you need is a long integer, something with twice as many bits, to temporarily hold the product. And then when you take the modulus here at the end, that will get you back to an integer size. So that's how modular arithmetic tends to get used. Now, there are ways that it gets used in practice. In particular, the value of C, or I should say the modular base, is commonly a prime number. And there's a lot of reasons for that. We'll see some of the applications for this later on. But basically, if C is a modular base, what that means is you can take a number modulo several different modular bases. And if they're all prime numbers, that means that they're all relatively prime to each other. And if they're relatively prime, that you're guaranteed that they're relatively prime. That's not the only way to get things relatively prime, but that's a way of guaranteeing that everything is. Obviously, if they're all prime, they're all relatively prime. And in case you forgot, relatively prime means the two numbers have no common factor between them. So even if they're not individually a prime number, there's no common factor between them. You would say they're relatively prime. Okay, so it's common to pick bases that are prime numbers because that makes it easier to avoid problems. So even if you think of like your hashing functions that might be in a hash table, the size of a hash table will often be a prime number because that makes it less likely that you are going to get something that's going to cycle. The cycle is going to generally have to be that prime number long in order for it to work, in the most general sense. So the the idea that's part of why I discussed primes at the beginning, was so that you knew this. And one particular example of this, let's say that we have some giant number. So let's say G is a giant number, and I mean a really, really giant number. And what we could do is we could take a bunch of modular bases, C1, C2, C3, C4, that are all different prime numbers. And if we want to know, is this giant number, perhaps is it equal to some particular value like 0, if we want to check whether a number is 0? Well, that might seem obvious, like, oh, shouldn't we know if it's 0? Well, you, like in the middle of a computation, you don't, right? This is a check that you're doing. You want to see, is some value 0? And in more general terms, if you're wanting to check whether A is equal to B, the way you would do that is A minus B and see if that's equal to 0. And so you might have computed some gigantic number here, and you want to see if it's 0. Well, you can actually do this probabilistically. Okay, so if G mod C1 is equal to 0, then what that means is in C minus 1 over C probability, it is 0. Okay, so that's what that means, is if G mod C1 is 0, then with C minus 1 over C probability, it's 0. So if C1 is like 10, okay, and if G mod 10 is 0, then 9 out of 10 times G is going to be, is actually 0. Now, 1 out of 10 times it's not, it's a multiple of 10. But you can see that if you have a very large value of C, a very large prime number, say, then the chances are that G is in fact 0, even though you're not absolutely guaranteed, you're pretty sure. And the more primes you have, the more this probability goes down. Okay, so if you then do G mod C2, and if C1 and C2 are relatively prime, then that means that this alone would say that, sorry, this was C1, this would mean that C2 minus 1 over C2 probability that it's 0, just from the second one. And so if I combine these two things together, I end up with C1 minus 1 over C1. Actually, the probability that it's 0 would be basically 1 minus 1 over C1 times 1 over C2. So it's a very small probability between those two. Okay. So that's the basic idea, is that you can probabilistically determine if something is 0 by having these modular bases. Okay, so this is going to get us to a really useful, interesting algorithm. It's one that you probably have run across multiple times already in your classes, and this is the GCD algorithm, or the greatest common divisor. So and the algorithm that we tend to use for this is Euclid's algorithm. And it's a very simple algorithm that I'll, at least in my experience, people very rarely explain why Euclid's algorithm works. They just present it. But I'll hopefully explain that here in a second. But the idea of the GCD, or using Euclid's algorithm, is that if you have GCD of A and B, and you get some result, and I'm going to, I guess I'll call it C. If C is the GCD of those, then what that means is that C divides A and B with no remainder. And what that means is that A mod C is equal to 0, and B mod C is equal to 0. So in other words, both of them, there's no remainder if they're divided by C. So keep in mind that saying that something divides something else means that there's no remainder when you divide one thing by the other one. Okay, so the way Euclid's algorithm works is we're going to just assume that A is greater than B. So that's just a base assumption that we have. And then we will perform one of two operations. So if B is equal to 0, then we just return A. So in other words, if we have to find the GCD of a number and 0, it's just that number, okay, by definition. Otherwise, we will return the GCD of B and A mod B. Okay, so this is the part that a lot of people, it's a very simple routine. That's it. That's the basic Euclid's algorithm. We're going to talk about the extended Euclid's algorithm in a minute. But many people, okay, they learn this algorithm, but you don't really see why. So let me just try to explain that really quickly so that you can see why this works. So we are looking for a value C that divides both A and B. So let's say that this is going to be our number A. I'm going to draw it as a figure. And let's say that B is some other value here. Okay, and what we're saying by C is this C is going to be some value that goes into these an even or an exact amount of times for each one. Okay, something like that. And that this might not be the best one. I'm not sure if I drew the right number there, but you'll get the sense. So if each of these things is of size C, okay, that C is going to be our divisor that can divide both of them. And so the thing to notice is if I have a number C that divides A and it divides B, well, clearly C still divides B, right? Okay, and it's also going to divide A mod B. In other words, if I sort of take off this, if I chop off this top part of A and take off all the B that's down there, what I'm left with, C still has to divide that. Okay, so in other words, it's still going to divide B just like before, and it's also going to divide A mod B. And if I were to draw something where, A was much bigger than B, so there's A and here's B down here, it might be that I have multiple B's that are there, but it's the same principle that there's still going to be, if something divides A, I'd still have all of these divisions. These would still line up exactly, and whatever is left over in A mod B is still divisible by C. Okay, so hopefully you can picture that in your head. You can see why Euclid's algorithm works that way. It's actually a pretty simple idea when you look at it. And this is an ancient algorithm. It's the oldest algorithm that we still commonly use in practice. Okay, so that's Euclid's algorithm. All on its own, you can use Euclid's algorithm to compute GCDs. One of the things that you can get from GCD is you can get the least common multiple between two numbers. So say you're actually wanting to create fractions and you need to know what the denominator to use is when you combine two fractions. You want the least common multiple of the two things. And so the least common multiple is A times B divided by the GCD of A and B. Okay, so the GCD of A and B is going to divide both A and B. Now, one thing that I will mention is when you do this, you always want to do that operation first, because sometimes if you were to do this operation first, it might overflow, whereas you're guaranteed that B or A divided by the GCD is going to give you that's going to give you a integer, and so then you can multiply by A and you're guaranteed that things won't overflow that way. Okay, so that's the basic Euclidean algorithm. The extended Euclid algorithm is an even more interesting idea, but we'll have to describe what this is. So the extended So the extended Euclid algorithm is a way of solving equations, and we'll see why you might want to do some of these in a minute. So this is a way to solve Diophantine equations. So when we go through this, and I'll give some examples, we'll see exactly how this works. But we need to describe kind of what a Diophantine equation is. So a Diophantine equation is where you have an equation like ax plus by equals c. And there is a theorem. The name of it is Bezout's theorem. Okay, and basically Bezout's theorem says that if D is the GCD of A and B, okay, so if D is the GCD of A and B, then D must divide C a solution. Okay, and I should have mentioned one other thing, actually very important here, which is these are all integers. Okay, so this is an integer equation. So we are going to be given A and B and C, and we want to find X and Y that are integers that make this true. And the only way that that's true is if C is divisible by the GCD of A and B. Okay, so I'll say that again. The only way that this is true, and this is Bezout's theorem, the only way that we can find integer solutions X and Y to a Diophantine equation like this is if C is a multiple of the GCD of A and B. Okay, and so because of that, what we will actually do is anytime we are given an equation like this, we will actually solve AX plus BY equals D, where D is the GCD of A and B. Okay, so that's what we're going to solve. And then since C is just some multiple of that, so C is going to be some number n times D. Notice that if we have a solution xy, we can say x prime is n times x, and y prime is n times y, and x prime y prime is a solution to our original equation, ax plus by equals c. Okay, so we can just multiply both sides by n, and we get back to the original equation, and we found integer solutions there. So we're not really constraining ourselves by making this the thing that we're going to solve. Now, sometimes when you do this, you don't actually know what the GCD of A and B are. I'll say there are applications, we'll see some in a little bit, where A and B are relatively prime, and therefore D is 1. Okay, so that's sometimes you'll see Diophantine equations written that way, where it's ax plus by equals 1, and the assumption there is that A and B are co-prime. They're relatively prime. Okay, so but anyway, that's the basic idea. So let's go through, and I think the best way to describe how to do this, or to show how to do this, is actually to describe the algorithm and then maybe show why that ends up working in the end. So the algorithm will kind of follow, it'll sort of take two stages. It'll follow the standard Euclid algorithm down. So the basic concept here is that we'll have the basic Euclid algorithm down to find D. And then that is going to set an X and a Y. And then we are going to sort of undo all the stages of Euclid's algorithm to generate new XYs at each level up until we get back to our original equation. Okay, so let me actually write this out as an algorithm briefly. So if we have extended Euclid of A and B, and we are going to assume, just like before, that A is greater than B here. And I'll just note that if we have a problem where B is greater than A, well, we can swap X and Y, right? There's no particular order in this equation for X and Y. And if one of them is negative or something like that, then we can just negate the whole thing. So anyway, all of this, it's very easy to make that assumption. We're not actually constraining ourselves by doing that. So if B is equal to 0, so just like before, if B is equal to 0, then we're going to return and we're going to return three values. We'll return x equal to 1, we will return y equal to 0, and we will return d equal to a. Okay, and so what does this mean? So let's look at this base case real quickly for a minute. What this means is that we have an equation ax plus by equals d. Well, if x has the value 1, and notice b has the value 0, and we just set 0 to y, and if this has the value a, well, sure enough, this comes out to a equals a. So that's like trivially an acceptable solution. So if you call extended Euclid with some value a and b is 0, then we can just return 1, and we can return 0 for y and a for d. A is our, remember, our GCD. And everything works just like we would expect. Okay, so that base case, it should be kind of obvious if you think about it. Okay, so otherwise, we are going to run extended Euclid of b and a mod b, just like before, to get x, y, and d. Okay, and d is just going to get returned, just like always. That's going to get returned, same as we did with the original value. But now here's the interesting part. So we're going to set x1 equal to y. We are going to set, and maybe instead of 1, let me do prime, just to clarify it. We're going to set x prime equal to y. We're going to set y prime equal to x minus b over a, a over b, not b over a over b times y. And it's important to note that this is integer division. Okay, so this is what we will have, and then we will return x prime, y prime, and d. So our values are going to be x prime, y prime, and d that we return. Okay, so notice that the d part of this d is going to be our GCD. That works just like the original Euclid's algorithm. There's nothing at all different here, so that should not seem something strange to you. So let me first of all run through an example of this, and then I'll explain it, and you can skip over the explanation if you don't really care about it, but I do want to give an example so that you can see it. So let's assume that we have an equation like 30x plus 12y equals 6. Okay, and we want to find solutions for x and y. Now, I will mention that there are an infinite number of solutions for x and y. We're going to find one of them, and I'll talk briefly at the end about how we get other choices from there. But we want to find an x and a y that make this thing true. And so we'll run the extended Euclid's algorithm. And notice 6 is the GCD of 30 and 12. So 30 and 12 have a greatest common divisor of 6. I already knew that, but you might not actually know that this is 6 to begin with. You just know it's some other value. Okay. So we're going to run extended Euclid. So I'll write it as EE of 30, 12. And when we do this, we will say, is b equal to 0? No, that's going to lead to us calling EE of 12 and 30 mod 12. So 30, 12 goes 24. The result is 6. The remainder is 6. Then we look at that. Is b equal to 0? No. We're going to call this again. We get extended Euclid now of 6, 0. Okay, so now we are at the base. So at this point, we are at our base case. We say if b is equal to 0, we're going to return. And so now what gets returned here is we have x equal to 1, y equal to 0, and d equal to 6. Okay, so that's what gets returned out of there. So now, as we come back up to this second level, this level right here, we're going to follow the steps that are outlined right there. So we are going to set our new x. This is going to be x prime, and I'll eliminate the prime in just a minute, just so that we can see it. We set x prime equal to y, so it's equal to 0, the value of y that we got there. And we set y prime equal to x, which is 1, minus a divided by b, so 12 divided by 6, which is going to be 2 times y times 0. And that comes out to be 1. And again, d is equal to 6. Okay, so that's going to be the values we return for x, y, and d. I will remove the prime just to prevent confusion. And now we go back up to the top level using these values. And again, we say x prime is going to be whatever y was, which is 1 in this case. And y prime is going to be x, which was 0, minus a over b. So 30 divided by 12, remember it's integer division. So that's a 2. The 12 goes into 30 twice. 2 times y, and y was 1. And so that's going to be minus 2. And so, and d is, of course, still 6. Okay, and so just to note this, I will take those off. And now we get our solution. We have x is 1, y is minus 2, and d is 6. And so if we plug this in here, we would see that 30 times 1 plus 12 times minus 2 equals 6. This is 30 minus 24 equals 6. 6 equals 6. Everything is exactly the way we want. Okay, so we found solutions. That shows you how this process works. So each time we call, we get back 3 values, x, y, and d. We recompute a new x and y and pass those back to the previous level, and we just sort of undo and work our way back, and we get a solution along the way. Now, before I go any further to describe how this works, let me just mention that any time, this is going to be true for all Diophantine equations. Is that if you have a solution x, y, so assume that x is a solution already, then x plus b over d times n and y minus a over d times n are solutions n. Okay, so no matter what value you pick for n, for all integer values n. Okay, in other words, once I have a solution like 1 minus 2, what that means is that I can keep generating new solutions by taking b over d and a over d and subtracting. And if you plug these in, well, okay, here, I'll do this and then I'll erase it just so that you can see it. But basically, remember that a solution means that we had that a times x plus b times y equals d. That was the solution that we had for x. And so if we were to substitute that and make this a of x plus b over d times n plus b times y minus a over d times n, that if I do this, I get ax plus ab over dn plus by minus ab over dn equals d. And sure enough, these two things cancel, and so we're left with our original equation. So that's basically why that works. But the way to think about it is basically we can generate an entire family of results for the Diophantine equations once we have one set of results. Okay, so the example that we have up here, notice our original equation was 30x plus 12y equals 6. So b over d, notice that this value is going to be 2. A over d, 30 divided by 6 is going to be 5. And so we can add 2 and subtract 5, and we get other solutions. So for instance, one solution that we had, the first one that we found was 1 minus 2. but we can get anything else that we want to by just adding on 2 and subtracting 5. So 3 minus 7, or 5 minus 12 would work, or we could go the other direction. We could have done minus 1 and 3 and minus 3 and 8, and all of those would work. So like minus 3 and 8, if we plug that in, we would get 30 times minus 3 plus 12 times 8. And so this is minus 90, and this is 96, and so the result is 6, just like we had before. So any of these results will give us 6. Okay, so Diophantine equations, we can use this to find all of them. So to find a whole family of solutions via this extended Euclidean algorithm. And we'll see one way that we can use Diophantine equations in just a little bit, but they come up in a lot of places. They're a big deal in cryptography. It's a way that you can look for solutions to certain crypto problems. Now, I do want to explain how all of this works just for a minute. So if you don't care about it, you can kind of skip forward in the video and until we get to the Chinese remainder theorem, which is the last topic. But if you're a little bit curious about why the extended Euclid's algorithm works, I'm going to go through that here for just a minute. So for the extended Euclid's algorithm, what we get when we actually have computed something at one level is we know that sort of the level below us, that's where we pan. Remember, when we call it with B and A mod B, right? That's the thing that we've called. And the result that we get back from there, well, let's call that X1 and Y1 and D. And D is just going to be what D is. And so what this means is that the first thing is that we have a solution where B times X1 plus A mod B times Y1 equals D. That's what we got from the very first piece of this. Okay, so if we were to now add onto this side, if I actually take this and I'm going to basically convert this, and where we want to end up at the very end is we need to show that basically A times X2 plus B times Y2 equals D. So for the thing that we actually care about, where we have extended Euclidean of A, B, what we need to do is figure out what are the X2 and Y2. What do we need to return from this, given that we've already computed that? So we know that that's true, and we need to figure out what can I return as X2 and Y2. Okay, so what we can do here is we can add on to both of these, we can add and subtract the same thing on both sides. So what I'm going to do is I'm going to subtract off B times A over B Y1, and over here I'm going to add B times A over B Y1. Okay, so notice I'm adding and subtracting the same thing on for both of these, and on this side it just remains D. Now, it's key to remember this is integer division, okay? So that's integer division. So over here on the left, this is probably the easiest part to see. On the left, we're going to get B times X1 minus B times A over B Y1. And this is equal to B times X1 minus A over B Y1. Okay, so that's what you get for kind of, that half over there. Okay, this other half is maybe the more interesting one. Okay, notice that we have A mod B, and we are adding on B times A divided by B. So I want you to think for just a minute, if I have a number A, and I do an integer division of A divided by B, what this gives me is this tells me how many times B goes into A completely. So that's going to be some value N, and the remainder is going to be A mod B. Okay. Okay, so now if I multiply N times B, I'm not going to get A back as a result, but I'm going to get A without the remainder. Okay, so whatever was left over as the remainder, I'm going to get n when I multiply n times b. In other words, when I do b times a over b, I'm getting everything that's there. So if I take something that is b times a over b, remember that is all of a except the remainder, and I add on a mod b, which is the remainder, the end result of that is just a. Okay, so this side over here is just a times y1. Okay, so that's the part that is maybe a little bit tricky to see, but that's what's there. And now if you look at these, what you have over here is you have a times y1. So what that means is x2 should get the value y1. And you have b times something over here. That's going to be your value y2. Okay, so in other words, the x that I return is the y that I got from the previous stage. The y that I return is x minus a over b times y from the previous stage. And that's exactly the algorithm that we had up here. If you remember, we have x prime is y and y prime is x minus a over b times y. So that's why that works. And the one other thing that I wanted to say about Diophantine equations is that we can compute something called a modular inverse. And one of the things that happens with modular numbers is it does not work for division. In other words, or it doesn't naturally work for division. So in other words, you can't say that I have a number a and I'm going to divide it by b, and you can't say that that's equal to a mod c divided by b mod c. That just does not work. I mean, b might be 0. I mean, yeah, that's not accurate. Okay, these are going to be fractions, they're decimal numbers, and so on. But what we can do is we can compute something called the modular inverse, because we sometimes do want to work with fractions and we want to work with them in modular arithmetic. And so what we're going to do is we're going to write this as a times b inverse. And b inverse is going to be the modular inverse of b. And in other words, what does it mean to have a modular inverse? That means that b times b minus 1 is equal to 1. In other words, if you multiply b times its modular inverse, you get 1. And if you write your numbers, so kind of the basic idea is if you write your numbers this way, if you represent your fractions as in this modular form, well, then you can actually do division just like you do everything else. You can write, you can do all of your you can do division by computing modular inverse and just multiplying by it. And then you can do all of your modular math even with division that way. It's very cool. Okay, but finding this modular inverse, we're going to use a Diophantine equation to do this. Okay, so the idea here is that if we want b inverse, this is the thing that we're wanting to find. And so what that means is sorry, I should have mentioned, this is that mod c. Okay, so when we take that mod c, the answer is 1. Okay, under modular math, that when you multiply these two things together. Okay, and so what that means is I'm going to call this thing x. So what I want is something where b times x mod m is equal to 1, and we want to find what m is. And so another way that we can write this is that b times x minus m times some number n, which we don't know what that is equal to 1. Okay, in other words, we're going to compute the actual product of b and x, and then we are going to subtract off, why did I say m? M is the modular base. I'll call it c. Sorry, I have notes that I was glancing at that used m. So we have our modular base. Basically, we compute the actual product b times x, and we're going to subtract off some number of c's from there, as many as we can, and we want the result to be 1. So that's what it means to have a modular inverse. And so we know what b is, we know what c is, we know what 1 is, and this, it should look to you, this is a Diophantine equation. Okay, and so you can solve this for x and n. So you can get both x and n via the extended Euclid algorithm that we just talked about. Now, if x comes out negative, or if x is greater than c, then you can do the adjustment that we talked about to bring x back down into the range of 0 to c. So then we will adjust the same way we talked about before to get x between 0 and c minus 1. Okay, so we're gonna actually get a value that's there. So to compute the modular inverse, we're going to solve a Diophantine equation and do the adjustment just like before, and that's going to let us do division, or the equivalent of division, even under modular arithmetic. All right, the last thing to mention is the Chinese remainder theorem. And the idea of the Chinese remainder theorem is you might have a very large number. So let's assume we have some large number x, okay? And this is a way of storing and working with very large numbers. And in fact, in many systems, this is the actual way that large numbers are kept underneath. You don't see it, but this is what's actually being done underneath. Okay, so the large number x, we are going to use a set of co-prime, and typically these are just plain old prime numbers, but the only real restriction is that they're co-prime. Set of co-prime bases, P1, P2, P3, however many we want along the way. And this is going to let us represent numbers that are as big as the product of P1 to Pn, like multiplying them all together. You can imagine you can represent any number that is as big as the product of those two things in this way. And what we will do is we will store the remainders. So we'll say R1 is x mod P1. R2 is x mod P2, all the way up to Rn is equal to x mod Pn. Okay, and the R sub i's are a unique signature for x. And the point here is only one number from 0 to product of all the p sub i's minus 1 is has that signature. In other words, there is only one number that if you take it mod all of these primes is going to have that particular set of remainders. And so if you know that set of remainders, you can actually do work with the remainders, and you can compute with the number. And so for instance, you can do something like check versus 0. If all of these are 0, you know that the number itself has to be 0, assuming the number is less than the product of all of your prime bases, which normally you have some restriction like that. Yes, I know, I can take, imagine that these primes are all like 9-digit primes. You can do lots of these. You've suddenly got a gigantic number, and you can check to see whether it's 0, and you can add numbers, and you can subtract numbers, and you can multiply numbers. You can do all of those things just like you would, just like we discussed before, but you're doing it with these remainders. Okay, so anytime you work with the number, you're going to work with each of the remainders modulo each of the prime numbers, and then you can do all of your math that way. Okay, and if you ever need to, what the Chinese remainder theorem actually says is that we can reconstruct x from the R sub i's. Okay, so if you have a way of actually storing x, in the end, if I give you a set of Ri's and the Pi's, you can actually reconstruct what x is. And so let me just give you one example of how that works. If we the first equation that we have where we say R1 is x mod P1, what that means is that x is going to be equal to P1 times some number N1, I don't know what n1 is, and plus r1. Okay, so for some integer. And the second equation is that x is going to be p2 times some number n2 plus r2. Okay, that's what each of these things are. And so since we know these two things are equal, what that means is that we can set these two things equal. And so we can get that p1 n1 plus r1 equals p2 n2 plus r2. We don't know n1 and n2 yet, obviously. Okay, and so we can rewrite this as p1 n1 minus p2 n2 equals r2 minus r1. And notice now that what we have here is yet again a Diophantine equation. Okay, where the unknowns that we have are n1 and n2. We actually know all of these others. We know prime base 1, we know prime 2, and then those remainders, we know each of them from the equation. And so from this, once we solve the Diophantine equation, we will get n1 and n2 from the extended Euclid algorithm. Given that n1 and n2, we will need to adjust. So the result is between 0 and p1, p2 minus 1. Okay, the product of p1 and p1, 0 and p1 times p2 minus 1. There's only going to be one value. There's only one possible n1 and 2 combination, so you can just adjust it. And it's either going to be going up or down, so you just have to, this is actually a pretty simple calculation to do. And you get the single result between them. And so now effectively what you have is you have that x, like another way that we can write this is we now have, we can say that x mod p1, p2, some new thing is equal to some new remainder, which I guess would be like, it would be like r2 minus r1. Actually, I'm getting confused about that part right now. You might have to recompute this. But anyway, the point is we're going to have some new single remainder here, R3. And you can call this thing P3, which again, if these were all prime numbers to begin with, they're all relatively prime numbers, and maybe P3 is not the best idea. Let's call it PA. Let's call this RA, so that we don't get it confused with the existing values. And then what we can do is we can take PA and RA and work with R3 and P3, and we can get another value. And then you do the same thing with R4 and P4 and R5 and P5, and you can gradually build yourself up until you find the final value X. Okay, so that's the Chinese remainder theorem. There are some somewhat more efficient ways of implementing that, and if you're really interested in fast implementations and things, you can look some of those up. But that's at least the premise. So let me just very quickly remind you of kind of everything that we looked at here. We started out, we talked about primes, and you see some of the reasons that we want primes are for things like this Chinese remainder theorem, and we need to know that things are, whether they're co-prime or not. We talked about how we would do modular operations, so all the different mod operations, and then in particular how we could compute the GCD and LCM, and this was with the Euclid algorithm. And then we talked about the extended Euclid, and we went to Diophantine equations. And we saw a couple of ways we can use them. We could use them to compute modular inverses. We can use them to actually just plain solve a Diophantine equation. But then the thing that we had at the very end was the Chinese remainder theorem. Okay, so that is our second group of math topics. There's one more. It'll be a short topic that I'll cover after this.